voices are reversed. What happened? And you're riding a new fish pond. Were you glad you were wearing your crash helmets? Yes, our previous display exploded when the professor touched it. Theory is that the tapered jar, marbles pressing down, warm afternoons and cold nights, jammed them in tighter and tighter. Poof! I had heard that antifreeze had fluorescene in it as a dye marker which responded to ultraviolet light. And I thought to myself, this could make a cool display. Very interesting. The green glass must be cutting out the ultraviolet rays. It's full of antifreeze and there's simply no display. Now let's try a piece of clear glass. Yahoo! Fluorescence. There it is. The perfect vessel for my experiment again. I don't know, the wife may notice this one. But it's my birthday, so she'll cut me a break. All right. We start with just a little ordinary water in there. Then we're going to add some antifreeze. I smell potential. Indeed, not looking too shabby just before the explosion. My wife said the first explanation I had for fluorescence ran 5 minutes and gave her a headache. So this is the quick version. Pitch is to sound as color is to light. So you can think of fluorescence as a high pitch smacking the outer electron shell of a molecule and making it ring in a lower pitch or a redder color. That's pretty much it. I actually got some tonic water with quinine in it. Now, how can we prove that we're really dealing with the outer electron shell playing around? Well, in here we have the tonic water with the quinine, and in here, we don't have Captain Morgan. We have some OxyClean, which is sodium percarbonate and sodium carbonate, both of which are strong oxidizers. What is oxidation? Oxidation is the loss of an electron. Reduction is the gain. Remember, oil rig is the mnemonic that can help you. So anyway, this ought to play with the outer shell and get rid of that free electron, because it's going to oxidize it. It's going to lose that free electron. And when that electron's no longer free to play the photonic Watusi, you notice the glow is gone. See, there's straight tonic water, oxidized tonic water. Keep the noodles fresh and the neurons firing. Enjoy, folks. This is a warning. The following section has been proven to cause headaches in certain individuals. If you find yourself beginning to experience a headache, please return to Professor Boz's Crazy Lab channel. Select Survival of the Cutest, and you'll be cured shortly. All right, let's talk about phosphorescence a little bit. This is how we're getting most of this display going. The first thing you got to understand is what a photon is. What is a photon? Well, light, heat, X-rays, gamma rays, ultraviolet rays are all just part of an oscillation in the electromagnetic spectrum. Now, for our purposes, we can just think of heat as a very slow wave. What we perceive of as red is a bit faster, green a bit faster than that, blue a bit faster, ultraviolet, and then you get up into X-rays and all the faster and faster rays. Now, I think intuitively we can all understand that just like swinging a hammer, the faster something oscillates, the more energy you've got in each one of those hammer blows. This is where the idea of quanta come from. The smallest piece of a wave that makes sense as a wave. If you slice a wave too small, you just have an instant. You don't have a wave. So a photon of light is the smallest piece of a wave that makes sense as a wave. So where does that bring us? Well, electricity flows through this wire. What is electricity? Well, it's a flow of electrons, and behind those there's an electrical pressure, electromotive force, voltage. That, in this case, is pushing the electricity through one-way valves, also known as diodes, and in this case, they're special diodes to emit light. Now, how does that work? Well, those electrons flowing through there go through a gap which has been doped with certain compounds. And those compounds, the outer electron shell is being excited, and then it is collapsing again in maybe 100 millionth of a second. And when it collapses, it is emitting a photon with the amount of energy that's proportional to the voltage that was used to go over that band gap. So a red LED might take 1 volt to light up barely. A green one might take 2 volts. A blue one might take 2.5, 3 volts. And an ultraviolet one like this, from what I understand, is 3.5 to 4 volts. So this represents a relatively fast-moving wave in the electromagnetic spectrum. So now one of those photons that's moving relatively quickly comes over here and strikes a molecule of fluorescence dye in this antifreeze, and that fluorescence dye, its outer electron shell, responds by kicking up to a higher energy state and then immediately collapsing, also in like 1/100th millionth of a second, give or take. And it releases a photon at a wavelength that we perceive of as green. Over here, it's absorbing and then letting loose a photon in the orange-red kind of bandwidth now, or band gap. I don't know what the compound is that makes that happen, but you could undoubtedly figure it out, because there's probably a compound that gives exactly that wavelength of light. This is how spectrography works. Anyway, I hope that helps your understanding of fluorescence. Remember, keep the noodles fresh and the neurons firing, folks. Love y'all.